Hey everybody, in this video we will go briefly into a topic called molecular orbitals. The molecular orbital, or MO theory, is basically a more complicated but precise way of thinking about covalent bonding. The topic itself is quite complicated, but in summary, molecular orbitals treat electrons as being a part of the whole molecule, hence that's why we call it molecular orbitals, instead of being a part of each atom, which is what we refer to as atomic orbitals. So electrons are part of the molecular orbitals, or the orbitals surrounding the molecule, instead of being part of the orbitals that surround the atoms, or the atomic orbitals. So before we begin, let's talk about this rule. The number of atomic orbitals combined must equal the number of molecular orbitals you have. So, for example, when you combine two s orbitals from two atoms, you create a bonding molecular orbital and an anti-bonding molecular orbital. So, in this picture down here, you can see that this will be your bonding MO, and this with the asterisk above will be the anti-bonding MO. Now, let's see how these things look like. So I'm going to use the red to indicate the nucleus. So for the bonding MO, you will have two atoms, and the electrons will be, well, right between them. Now, for an anti-bonding, as implied by the name, the electrons are not going to be bonding. So instead of bonding, they are going to be apart and not in between the two nuclei where they're supposed to be when they're bonding. So this is a visual representation of how the bonding and the anti-bonding MOs look like. So anti-bonding again just means that the two electrons are not between the nuclei and thus are not bonding. So this diagram itself is an orbital diagram that shows the electrons ordered from lowest energy to highest energy, and instead of it being in atomic orbitals like we've done before, this time we order them in these MOs that are in the middle. And if you notice, we also have 2p orbitals, and these 2p orbitals combine to form a total of 6 molecular orbitals. So 3p orbitals here and 3p orbitals from the other atom. That means a total of 6p orbitals, and thus you have 6 molecular orbitals, because according to the rule, the number of atomic orbitals must equal the number of molecular orbitals. So in this case, you can see that there's a sigma right there and a pi right there. These represent sigma and pi bonds. And remember, in a triple bond, such as over here, there are 2 pi bonds and 1 sigma bond. So that's why we have one box with 2 electrons for the sigma bond, and 2 boxes for a total of 4 electrons for the 2 other pi bonds. So let's actually read on and see what else we can learn from these MOs. So we just said that we fill the MOs from bottom to top, and even though the anti-bonding molecular orbital is not very stable, and in reality it actually decreases the stability of the molecule, it must be filled since it is lower energy than the other MOs above it, and this is in accordance to Aufbau's principle. And also note that when you fill these MO diagrams, you also have to follow Hund's rule, which is when you do everything single before pairing them up. And this might be vague, but we've talked about this. So over here, in the same sublevel, they made sure that the electrons were unpaired before they started pairing them. So all the orbitals here are unpaired, so you could technically start pairing them up now, but since there are not enough electrons, then you don't pair them up. So let's see what else we have to read about. So MO diagrams are done with 2 atoms connected by a covalent bond. So you tend to do MO diagrams with 2 atoms at a time. And this is what I said over here. Now, MO diagrams help us determine something called the bond order, which tells us the stability of the bond and sometimes, but not always, tells us the type of bond, which is single bond, double bond, or even a triple bond. So before we continue, let's erase all this and talk about how this MO diagram was created. So this MO diagram is showing O2, and O is on this side and O is on this side. And notice how we're only looking at the 2s and 2p levels. So because we're only looking at those two levels, then we're technically just looking at the valence electrons if you think about it. So if we're just looking at the valence electrons, which is what we typically do with MOs, then you'll see that there are 6 valence electrons here and 6 valence electrons here. And as a result, we actually combine them to make a total of 12 electrons total for the molecule. And we kind of fill these 12 electrons up. So there's 2 there, 4, 6, 8, 10, and then 11 and 12. So notice how there are 12 electrons in these MOs, and that's how you fill these MO diagrams. You fill them from the bottom to the top. Now that we know how to do this, let's talk about the formula for finding bond order. The formula for bond order will be the number of bonding electrons, or the ones that don't have the star, minus the number of antibonding electrons, or the electrons that are in the orbitals that have stars, and you divide all that by 2 to get the bond order. So for O2, the bond order is the number of bonding electrons, which is 2, 4, 8. So we have 8 bonding electrons. And how many antibonding electrons? Well, there's 2 and another 2, so there's actually 4 antibonding electrons in the O2 molecule, and you do 8 minus 4, and then you divide all that by 2, and you get a bond order of 2. And this corresponds to a double bond. And note that this doesn't always work, but for this case, the bond order of 2 indicates a double bond. Now, we also use MO diagrams to help us determine whether a molecule is paramagnetic or diamagnetic. So as a review, diamagnetic means that there are no unpaired electrons, and paramagnetic means that there are unpaired electrons that exist. And we use the MO diagrams to help determine this, just like how we did it for the atoms in the chapter about electrons. So in this case, O2 will be paramagnetic, since over here we see 2 unpaired electrons in the anti-bonding pi orbitals, or pi molecular orbitals to be more specific. So before we move on, I want to point out something. This MO diagram over here only works for atoms in period 2, since atoms in period 2 have their valence electrons in the 2p and 2s sublevels. It won't work for period 3 because those atoms have their valence electrons in, 3s and 3p. But the thing is that you could actually use MO theory for any period, and all you would have to do is just change the 2s and 2p to something else, like maybe 3p and 3s, and it would still stay the same because the template for this diagram is the same. So in the end, you basically have 2 s orbitals on each side forming 2 MOs in the middle, and then you're going to have 3 p orbitals on each side forming a total of 6 MOs in the middle. Now your job is just to memorize how it looks like. So sigma, and then sigma with anti-bonding, and then sigma, and then 2 pi, and then 2 pi anti-bonding, and then sigma. So if you want to think about it this way, just think of it as a mirror. So this is a mirror image of that, and this is a mirror image of that, since the pi's are like that, and the sigmas are like that. And notice how the anti-bonding orbitals are always higher in energy than the bonding orbitals. So keep a note of that, or simply just memorize this format right here, and you'll be able to do it for anything. So let me give you an example. The first example that we are going to do is not going to be N2. Instead, we are going to do H2, so I could show you how this can be applied to any period. So H2 will be 1s and 1s, of course. Just like in the diagram, instead of 2s, we have 1s now, but there are no 1p orbitals, so we just ignore all this for H2. So let's think about this. So let's put the 1 electron, since there's 1 electron in the 1s orbital for H in H2. So when we combine this, we get something that has lower energy, which is going to be our bonding orbital, and this will be our sigma, and then we are going to have an anti-bonding, and that will be indicated by a sigma with a star. And I think I'm right about that, since if you look at the previous picture, it kind of looks like that, so we're good there. So when we combine it, of course, we know that there's 1 electron each side, so we have 2 electrons total. So we simply have to go 1, 2, and we're done. So this is the MO diagram for H2. So let's calculate the bond order. The bond order is the number of bonding electrons, so 2, minus the number of anti-bonding electrons, 0, and divide all that by 2, and we get a bond order of 1, which actually reflects the structure of H2, since H2 is bound together by a single bond. So now let's do it for another. Well, actually, before we finish, is this diamagnetic or paramagnetic? I think it's going to be diamagnetic, since there are no unpaired electrons in this MO diagram. So now that we're done with that, we can do it for another molecule. And let's clear the ink, and now let's talk about He2. You've never heard of this? Well, that's probably because it doesn't exist. Can helium really form a bond with another helium atom? Well, we could show this by doing MO theory. So helium and helium. Well, let me not put helium there. Let's put it like up here. So helium has 2 valence electrons. So 1s and 1s. So 2 there and 2 there. And they go like this. So they're going to form sigma bond and an anti-bonding sigma, and just like that we have a total of 4 electrons. So we are going to fill this ladder, so 1, 2, 3, 4. So let's determine the bond order. The bond order will be, well, let's see. So no, it won't be 4, it will be 2 bonding electrons minus 2 anti-bonding electrons, all divided by 2, we get 0 for the bond order. And the bond order of 0 tells us that there will be no bond between helium and helium, so therefore He2 cannot exist since the bond order is 0, telling us the bond between H2 will be pretty unstable. Now, is it diamagnetic or paramagnetic? Well, it's going to be diamagnetic once again because there are no unpaired electrons. And now that we're done with these 2 examples, let's do it for N2. Let's draw out the structure for N2 and try to predict the bond order from the structure. And keep a note that this does not always work. So in order for it to work 100% of the time, we have to use the MO diagrams and not this method I'm going to show you. So I think it's going to have a bond order of 3 since it's a triple bond. So let's see if our predictions are right. So N will be having 2s and 2p electrons, so we have to copy this entire diagram. So we have to have 2s on each side, and of course we have nitrogen on each side, and then 2p 3 times, since there are 3 2p orbitals for nitrogen, and we have to combine them. So we combine it like that, and let me try and make this look as nice as possible. So this is the anti-bonding, this will be the normal one, and then same goes for here. So this will be the normal one, and then for here, what will actually happen is that you'll have 2 spots for the pi bonds, and then you are going to have the anti-bonding pi orbitals, and then you are going to have, last but not least, the anti-bonding orbital for, you know, the sigma bond. So it looks like that, a little messy, but we could deal with this. And let's try to figure out how many electrons we have in total. So 5 electrons for nitrogen, because nitrogen has 5 valence electrons, So let's do that for each nitrogen. And now that we've done that, let's combine them together. So we know that there are a total of 10 valence electrons. So let's go up the ladder. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Seems like we got everything, and now let's calculate the bond order. The bond order is the number of bonding electrons, so 2, 4, and 8, minus the number of antibonding electrons, 2, all divided by 2, and we get 3. So the bond order is 3, and look at that, it predicted the type of bond. But note that this does not always work, but this time it did work, so hooray, right? Now, is this paramagnetic or diamagnetic? Well, there are no unpaired electrons, so this is diamagnetic once again. So that's all for N2, and now let's move on to the next question. So we are going to look at carbon monoxide, and this time, since my writing is super messy, I'm going to use a template for this. So instead of being O and O, we are going to have C atom and O atom, and the molecule will be CO. So now we have to change the electrons, of course. So I think all we have to do is just cover this electron up and this electron up. And now we have 4 valence electrons and 6 valence electrons here. And okay, so in order to do the MO diagram for this, the total number of valence electrons is 10. So 2, 4, 6, 8, 10. So we remove these two. Okay, let's calculate the bond order. So there are 2, 4, and 8 bonding electrons minus 2 anti-bonding electrons, which is right there. So you divide this all by 2, and you get 3 once again. Now let's try to draw the Lewis structure for CO to see if this agrees with what we predicted. So let's see what CO looks like. So CNO. Now let me think about this. If we make carbon gain an electron, then it will need 3 bonds, and if oxygen loses an electron, it will need 3 bonds. So I think I'm going to give this a positive formal charge and a negative formal charge, and this will allow us to put a triple bond between them. So let me put the lone pair there, and let's see if the number of electrons is correct. So there are 2 lone pairs and 3 bonds, so that's 10 electrons, and that matches that number, so we're good. So this Lewis structure is correct, and it tells us that carbon monoxide might be a bit unstable, but it still exists because it has a bond order of 3, and there's a triple bond there, so look at that. The bond order predicted the type of bond again, but note that this does not always work, as we'll see soon. And CO will be diamagnetic since there are no unpaired electrons. So let's move on to this question, Br2. So Br has an electron configuration of, I'm guessing, well, let me look at a periodic table. I'm pretty sure it is going to be argon, and then it's going to be 4s2, 3d10, and then 4p5. So looking at that, I think I know how to draw my MO diagram. So these will not be 2p or 2s. Instead, they will be 4p and 4s. And let me do that for the other side. And instead of O's, we will have BRs on both sides. So we will be looking at the bromine molecule here. And let's fix the number of electrons. So 7 electrons, 7 valence electrons, since we're not looking at the d electrons, because the valence electrons for the main group elements are going to be our outermost s and p electrons. So there are 7 of them, so 1, 2, 3, 4, 5, 6. So let me just add 1 more. And let me put a down arrow for that one. And then let me put another down arrow for that one. So notice how the pair is at the end instead of at the front. I mean, if you put it either way, I think it would be fine. So now let's see how many total number of valence electrons there are. There are 14 valence electrons total. So there are 2, 4, 6, 10, 12, and we have to add 2 more. And now we have 14. So now let's find the bond order. So the bond order will be, well, the number of bonding electrons. So 2, for 8, so 8 minus the number of non-bonding, or anti-bonding electrons. So the anti-bonding electrons will be 2, and then 6. So 8 minus 6 all over 2 is going to be 1. Now this predicts the single bond between two bromines, and look at that, it works. So it won't always work, but for this case, it actually worked. So is this paramagnetic or diamagnetic? Well, I think this is going to be diamagnetic, since there are no unpaired electrons. Now let's take a look at one more example, nitrogen monoxide. So let's try to draw nitrogen monoxide. So I think I'm going to fill the octet for oxygen first and leave nitrogen hanging, so it will kind of look like that. Or you could do the resonance structure and see that it will look like this as well if you wanted to. But this time the nitrogen has the octet while the oxygen doesn't. So these two are going to be resonance structures, and it seems that this will have a positive 1 formal charge and this will have a minus 1 formal charge. So let's find the bond order for NO. So NO will be here, and we will change the O2 to NO. And N has 1 fewer valence electrons than oxygen, so we'll just remove that one there. And in the end, we have a total of 11 valence electrons, so 2, 4, 6, 10, 11, so we remove one of these, and we're left with this. So now let's find the bond order for NO. So we are going to have bonding electrons, so 2, 4, 8, so 8 bonding electrons minus anti-bonding electrons. So the anti-bonding electrons will be 2, 3. 8 minus 3 over 2 is going to be 2.5. Now you're like, wait a second, why is it a decimal? Well, it's a decimal because bond orders can be decimal numbers, and it does not reflect the double bond between N and O. And this is why I've been telling you that the thing that you do by just looking at it, it doesn't always work, but it works sometimes. But in this case, it did not work. So NO has a bond order of 2.5, and it will actually be paramagnetic. And the reason being is that there's an unpaired electron in the anti-bonding pi molecular orbital right there. So this goes to show that the bond order can sometimes be an unpredictable number that you never expected. Now note that this method only works when you have 2 atoms. So if you have a diatomic molecule, and the 2 atoms can be different, of course, then you're good. But if you have something like CO2 or something that has 3 or more atoms, then you're in trouble because this method doesn't work because there are too many electrons to fit into this diagram if there are ever 3 or more atoms. But if there are 3 or more atoms and you're asked to determine the bond order, here is a crude trick that sometimes works but sometimes doesn't. So use this with caution, and if you have no choice, just use it. So for example, if we have carbonate, you know that carbonate is going to be pretty hard to fit into an MO diagram since there are too many electrons in carbonate. And if you take 2 atoms at a time, I'm afraid that things get too complicated and it gets super confusing. Carbonate looks like this. So you're going to have this, and then you're going to have a negative formal charge there and a negative formal charge here. And you might be at first like, oh, this is easy. This has a bond order of 2, this has a bond order of 1, and this 1. Now, this is wrong because this molecule actually resonates. So in the end, the resonance hybrid, which we learned in a previous video, will look like this. And from there, you realize that these 3 bonds are actually technically the same since they are resonating and kind of sharing that pi bond around. So we treat these 3 bonds equally. But how do you find the bond order? Well, to find the bond order, you have to first know that, of course, these 3 bonds are treated equally. And then, from there, you can do something. So let me erase all this and redraw this. So this will be a single bond, a double bond, and a single bond. And let me redraw the lone pairs to make them there again. So it looks like that. So you know that these three bonds are treated equally since they resonate. And because of that, you could simply do this. So you take 2 plus 1 divided by the number of bonds, which is 3. And you get a bond order of 1.33, and that would be the bond order for a carbonate. Now, this method works for most cases, but not all cases, so be careful when you use this. Now, let's try CO2. So CO2 is quite easy, so it looks like that. Oh, I drew it wrong. It actually looks like this, and it has 2 lone pairs on each oxygen, and from here, you can determine the bond order for the bond. And since carbon dioxide does not have any resonance structures, you can simply just look at the bond and say, oh, this is 2 and this is 2. So the bond order of each double bond is going to be 2, and that's all you do. So these assumptions are usually right, but they're not always right. So be careful whenever you use them. And that's all for this video, and have a nice day.